All right, today we're going to be talking about solutions. And so we're going to talk about not only the parts of solutions and definitions around solutions, we'll also be talking about electrolytes and some properties of solutions or how you make them. Okay, so the first thing is talking about solutions. What is a solution? Well, we're going to say it's a homogeneous mixture, which means that it's uniform throughout. There's going to be only one distinct phase. And some examples are going to be, coffee, salt water, sugar water, your Gatorades are solutions. It's pretty much endless. If there's something in water, it's a solution, and it doesn't have to be water. It could be other liquids, but as water being a common example for us, anything in water would be a solution. Okay, and so there are two components to a solution, and that is the solute, which is the substance that is being dissolved in the liquid, and the solvent, which is the dissolving medium. So the solute would be the salt, while the solvent would be the water. Okay, so when we talk about, the solute, that's whatever we're putting in, and the solvent is what we're putting it into. And the solvent is going to be the thing that really determines how this works, as it's the properties of the solvent that allow a solution to form. Okay, so ion concentration. So ionic compounds dissociate into ions when they form these solutions. And so when solutions are formed, you have these ionic compounds that are going to dissociate, which means instead they break apart. Okay, so dissociation, a process by which molecules or ionic compounds break down into smaller particles. So what we're seeing here is that you have these negative ions, these positive ions, kind of breaking off and being stabilized by the solution, which is the water. In this case, we're using salt water. And so when we have this sodium chloride, they're actually breaking down into their aqueous forms, which means they have dissociated. It is a little bit different than dissolving. Ionic compounds are not going to dissolve, they're going to dissociate. So dissolving is like sugar going into water where the sugar molecule stays whole. But under dissociation, those compounds are going to break down into their individual ions. So, leading us into aqueous solutions. So water is the universal solvent. And so it's because water is polar. And so it has this strong dipole between those oxygen hydrogen bonds, which then allows these polar things to grab onto uh, the things we're trying to dissociate, right? Because that bent structure, because of the oxygen hydrogen, we get hydrogen bonding, which allows an ion dipole interaction, all right, which we have talked about in class, and we said that the slightly negative charge of those hydrogens is going to grab onto the positive charge of like a sodium, and the slightly positive or the slightly negative charge of uh, slightly positive charge of the hydrogens is going to grab onto the negative chloride. The slightly negative oxygen is going to grab onto the slightly positive or the positive sodium. And so we call this the ion dipole interaction, which is very clearly that the ion in salt, in this example, the sodium or the chlorine, is going to directly interact with that dipole, that slightly positive or slightly negative part of water. And then it interrupts that dipole-dipole interaction. And because of this, we make an aqueous solution, which is a solution which the solvent is water, and we have something in the water. Okay, the solvent is water, though, which makes it aqueous. Okay, we noted that on the last slide by that little AQ down at the bottom of the sodium chloride right here, where we had sodium Na plus AQ and Cl minus AQ. That means that they are aqueous. Okay, and so now we have electrolytes. And with our electrolytes, we're going to talk about three different things. The first would be a non-electrolyte. So dissolve only as a molecule, does not conduct electricity. So the thing that's going to go into solution here is dissolving, but it is not dissociating. So it's not like the sodium chloride that breaks up. It is staying whole as a molecule. There is no dissociation. Therefore, there are no charges in solution. You get a weak electrolyte, which means that some of it dissociates in water, but not all of it. And so they dissolve mostly as molecules, but some of them will break up. These are things we're going to learn to be called weak acids or weak bases, where these things don't necessarily dissociate in water. They don't fully break up. A lot stays as that molecule. And then as the ions are being used, more can dissociate over time. And the last one would be a strong electrolyte. And strong means that it is 100% dissociation. This is something like, sodium chloride, table salt. It dissociates 100%, meaning it is a ton of ions in there, and it is a very, very strong electrolyte. An electrolyte, the term just means that it is a solution that conducts electricity. So when we have a non-electrolyte with that molecule, you can't have this, there's no electricity that will pass through that solution. So if we dip two wires in, we would not have electric passing through if it is a non-electrolyte. As soon as you go up to an electrolyte, whether it's weak or strong, you will now get where electric will pass through that solution. With the weak electrolyte, less electric will pass through the solution. With the strong electrolyte, most of it will, if not, full transmittance of that electric. Okay, so now we're going to talk a little bit about solubility, which has to do with how much dissolves. So when we're talking about making solutions, we're going to say that the solutes dissolved in the solvent, and there's something called dissolution rate, which is the rate at which a solute dissolves. If in our head we can compare, think about sugar in water versus salt in water. If you had room temperature water or cold water, these things are going to dissolve at drastically different rates. Okay? And so we can increase that dissolution rate by a few things. Think about, how do we get the sugar to completely dissolve in water, right? We've all had an unsweetened iced tea or something like that and put a sugar packet in and stirred it, and the sugar just does not dissolve, right? Or you're making, some sort of like pre-mixed beverage, let's say, some sort of Kool-Aid or Gatorade, and you use cold water to start, and you're mixing up, or ice water to start, and you're mixing up, and it's just not dissolving. And so there's a few things that we can do. And the first thing is we can increase the temperature, right? If we have it hot, that sugar dissolves right into solution. All right, it gives us no problem at all. We can increase the kinetic energy, which is stir more, which I'm sure all of us have tried, right? We're stirring and stirring, we're adding energy into that solution. Or we can increase the surface area of the solute, which means that you could take like a like a sugar and grade it down so it's smaller particles. There's more surface area, there's more interaction between the solute, what's dissolving, and the solvent, what it's being dissolved in. So that water sugar interface occurs just more. Okay. And then solubility is defined as the maximum amount of solute that dissolves in a specific amount of solvent. So if something is highly soluble, it means a lot of it can dissolve. Think salt. You could really pack salt into water, right? It's highly soluble. Slightly soluble would mean that only a little bit will dissolve. Sugar water, right? We've seen that. We've poured it in the sugar, we've stirred around, sugar stays in the bottom. It's slightly soluble. Some of it will dissolve into solution, but some of it won't. And then there's insoluble. Think about when we put in, really anything that doesn't dissolve in water. You put in, metal flakes into water, it wouldn't matter. But whatever you put, it's not dissolving at all. None of it is going into water. It is insoluble, right? Your containers, if you have a water bottle, the plastic, the metal it's made out of, no matter how much water you put it in there, you're not going to dissolve it. It's not going into solution, right? That would make sense. It's an insoluble particle. However, it may be soluble in another medium, right? So styrofoam can hold water, right? If we get a styrofoam cup of coffee, it'll stay there. It won't break down the cup. But if you were to pour in certain solvents like gasoline, it readily breaks down styrofoam. It'll eat it right up. It'll dissolve it right into solution. And so, depending on what we have, what we're talking about, they're soluble or insoluble in different solvents. So the rules change. Okay, salt is not soluble in certain solutions. Sugar is not soluble in certain solutions. It all depends on what you're mixing here. Okay, now saturated versus unsaturated. So we talked about this word a little bit with those Pogles, but what are we really getting at here? And it's that saturated solutions contain the maximum amount. These are, we have dissolved everything we can. We can't possibly dissolve any more into this solution. They are completely saturated with it. And so if we look on the right hand side, we can see, well, we've been pouring in salt and mixing this thing up, and we've gotten to a point where no longer will the salt dissolve, right? It's settling down the bottom, which what's happening there is some of it's dissolving, but as it's dissolving, some of it's recrystallizing. And so you get this movement where some's going into solution, some's coming out, but that's happening at the same rate, okay, where they have this, again, this undissolved bottom layer where we're having no more will dissolve. Then you have supersaturated solutions, which would be that you've dissolved more than is allowed. And that's by using some of those principles of how do you increase solubility? Well, some of it is that you are increasing the temperature. You can turn that temperature up, dissolve more into it, and then bring that temperature down. And it's now a supersaturated solution. It is holding more than it's supposed to, which means that depending on what you do, it'll jump out of solution just like that. So think about if you've ever made like sugar, like rock candy. You heated the water up, you dissolved as much sugar as you can, just kept on forcing it in there. Now you have this crazy saturated solution at a high temp, boiling. But then you allow that to slowly cool. And now it's at room temperature, and there's more sugar in there than should be. And that's a supersaturated solution, which is why when you dip that string in, candy starts to form. Okay? And unsaturated would be we're not at that rate of saturation yet. It is anything less than. There is some dissolved, but we haven't hit the limit. Sorry. All right. Now, we have solubility is very, very, very dependent on temperature. As we increase the temperature, things will rapidly more so dissolve. Okay. But that's not everything. Okay. Because it's not, solubility is not only solids into the solution. Okay. Solubility is going to increase for most solids, more so as temperature increases. It's not, it doesn't necessarily do it with salt, for instance. If you're looking at that solubility curve there, it stays relatively flat. More will dissolve, but negligibly so. It doesn't increase it a whole heck of a lot. Okay, whereas like glucose, you'll see that sharp curve. As temperature increases, man, glucose dissolving a whole lot more. However, it's going to solubility is going to decrease for gases. Water holds on to gases like carbon dioxide, nitrogen, oxygen, right? We know there's oxygen in water. It's how the fish breathe, right? And so when you heat up water, all those gases are pushed out of solution. When you boil water, there's no longer carbon dioxide in that water. There's no longer oxygen in that water. You've gotten rid of everything. And this is exactly what happens with things like climate change, where they're worried about it. We have these oceans, which are giant carbon sinks. They hold on to it all, they trap it in there. But as global temperatures of seawater rise, they hold on to less carbon dioxide, meaning more is in the atmosphere, which causes more heat to stay in, which then causes the water to heat up more. And we're in this vicious cycle of greenhouse gases and climate change. All right. Equally so, when you have like a nuclear plant that uses, the cooling towers and they release hot water into the bay, depending, or the ocean or wherever they're at, okay, a river, you end up seeing a dead zone for fish. Nothing can survive in this area because there's no oxygen in the water being released. Okay, so depending on it, the regulations around it, but this is what happens, and so we can see the solubility curves here. And you got introduced in the POGIL. It's just you saw one more so like this, where everything's going up, but with gases, it's going to go down as temperature increases.